All right, 2.2, finding equations of linear models. All right, so when we're doing this, what we're going to do now is, instead of looking at raw data that we looked in the previous section, we're going to look at how to get data, or how to get this information from descriptions and from doing it by hand as well from raw data. So we're going to have raw data itself in a problem later on, but how do we get a linear model, not just from a graph, but how do we get it by hand? So from a description, so let's look at this one. So if I have a description and I want to get a linear model from an actual description, and you'll see later getting a model from data by hand, they're going to evolve using the techniques that we learned in chapter 1. You know how to find the equation of a linear model. Use the slope formula, and you could either use the point slope form or the slope intercept form. Either one will work, as you already know. Okay. So if we read this example, it says the number of Americans who have a passport has increased approximately linearly. So that's a key piece of information there, because that tells us that the data has a linear relationship. And it goes from 11.1 million in 1990 to 109.8 million in 2011. Here's the variable's description right here. This is big, because this tells us which variable is which. Let n be the number in millions of Americans who have a passport, and t is the years since 1900. Find a linear equation. Okay, well, so we got to identify the independent and dependent variables. Now the independent variable is going to be t here, because it's t years since 1900, and the number of people, or the number of Americans who have a passport, depends on what year you're looking at. So the independent variable here is t, and the dependent variable here is n. So in other words, x is being treated as t, and y is being treated as n here. Okay. So now that we know that, if I want to find an equation of a linear model from this information, that means I want to get something that looks like that. Y equals mx plus b. How do I do that? Well, I need two things. I need a slope and a y-intercept. Or I could use point slope form. This is slope intercept form. This is point slope form. Remember those two different, either one is fine, but you could either use this one or this one. But either way, I'm going to need a slope, and here I'm just going to need an ordered pair, x1, y1. Either one will work, and it's up to you. So either one will work just fine. All right, well, I'm going to need a slope. So how do I find the slope? Well, that's this formula, y2 minus y1 over x2 minus x1. Now, in this problem, like I said a moment ago, the independent variable, which is typically x, we're treating that as t in this case. And the dependent variable, which is usually y, we're treating it as n in this place. So just to make just to make this problem more consistent, I'm going to replace the y and x with their corresponding variables, t and n. So, dependent is y typically, so this is going to be n2 minus n1 instead. And x in this case is t, so it's going to be t2 minus t1. That's only because of the problem has these variables in lieu of x and y. That's it. That's why it's important you got to know which one's independent and dependent, otherwise you can mess up here and swap these incorrectly. That's why you have to make sure of this. Okay, so how are we going to get this information? Well, it's right here. So it goes from this amount to this amount. So this is the first amount, and this is the second amount. So in other words, we could think of this as the N2T2 point. We could think of this as the N1T1 point. Well, actually, I said that in reverse order. This is the T2N2. This is the T1N1 point. Because we go from the first point to the second point, right? So N represents the number of 1 million Americans have a passport. So if it goes from this to this, then this 109.8, and it's in millions, so N2 is going to be 109.8. And that's going to be in the year 2011. Now, that's going to be 2 years since 1900, so it's going to be 2011 minus 1900. All right, so let me jot this down here. So 109.8 million in 2011. So as an ordered pair, well, 2011, right? T is the year since 1900. So 2011 minus 1900 is the year, well, is the number is 111 years. So as an ordered pair, T2, N2, right? Because this is independent, comma, dependent. Independent, comma, dependent. So that's the number of years since 1900. Well, that's 111, comma, and number of Americans with a passport in millions, which is going to be 109.8. All right, so that's how we take this data and we, put it in the form of our independent and dependent variables as an ordered pair. Now let's look at this one, because we go from this to this, so that's why this one's the second one. That's why I use the second one. This is the first one. That's the starting point. So 11.1 million in 1990. That's the first order pair. So that's T1, comma, N1. So 1990 is how many years since 1900? Well, that's this minus that, which is 90, comma, and 11.1 million. So here's our two ordered pairs. Hey, we have two ordered pairs now. Guess what? We could find the slope. If you have two ordered pairs, you can find the slope. So let's do that. So now it's just a matter of plugging them in. So N2 minus N1, so that's going to be 111. So N2 minus N1 is going to be, I'm sorry, I said the wrong number. It's going to be 109.8 minus 11.1 all over T2 minus T1, which will be 111 minus 90. So since we're working with decimals here, it's using your calculator is pretty is a wise choice. So 109.8 minus 11 point, that's 98.7. All over 111 minus 90, which is 21. So now, when I take that and I put it in my calculator, so 98.7 divided by 21 gives us 4.7. All right, so that's our slope. That's our slope. Now, our goal here is to find an equation that describes this data. So when I find an equation, like I said, I need a slope and a y-intercept, or I need a slope and an ordered pair. Well, at the end of the day, either one of these will get your result, but it just depends on what information we have. And based upon the information that we have in this problem, I have a slope and I have two ordered pairs. So which one do you think I'm going to use? I'm going to use this one, because with the point slope form, I just need a slope and an ordered pair. I have two ordered pairs. I have more than I need. So I'm going to use the slope that I just found, and I'm going to use one of the ordered pairs. I'm going to use this one. So I'm going to use this. That's what I'm going to use. So I'm going to choose this ordered pair with that slope, pop them in here, and then go from there. So now, again, I could make the substitution as y for n and x for t. I'll do that again. So this will be n minus n1 equals m times t minus t1. All right, so now with the n1, you're just going to replace it. This n1 and t1 doesn't necessarily mean this order pair. It could mean this one. Don't confuse that. That's just happens to be the point I'm picking, but it could be this one. That's fine too. That's just where you're going to substitute the coordinate values. That's all it means. So n1 here was going to be n1's going to be 11.1, and that equals the slope, which is 4.7 times the quantity t minus, and then t is going to be 90, right? T1 is 90. All right, so now it's just a matter of, so again, think about in chapter 1, when you plug them in, then you just distribute the slope out, and then you're going to solve for the dependent variable, which in this case is n, or typically it'd be y, right? So, all right, now just distribute the 4.7 to here and here. So n minus 11.1 equals, so 4.7 times t is 4.7t. 4.7 times minus 90, it's going to be minus, so calculator time, 4.7 times 90 gives me 423. Okay. And then so then the last thing we do here is we're going to add 11.1 to both sides so we could get n by itself. So n is going to equal 4.7 t minus 423 plus 11.1. So negative 423 plus 11.1 is going to give me minus 411.9. So that right there is our linear equation that models this data. So yeah, that's how you would get that linear equation. And again, if you wanted to find the y-intercept instead, well, here it is right here, because this is in slope-intercept form, right? At the end of the day, when you solve this for y, you're going to get it as mx plus b. mx plus b. It just happens to be a negative y-intercept. Okay, so my slope is 4.7, and my b is going to be negative 411.9, which is approximately 412, negative 412. But just leave it as a decimal, that's fine, because we're working with decimals, you might as well leave it as a decimal. Again, you could graph this thing just to get an idea of what it looks like, but we have nothing to compare it to because we don't have data in this case, we just have ordered pairs. But 4.7x minus 411.9. I might have to modify the I might have to turn my stat plot off. I do. Alright. And I might have to modify my zoom button on my calculator just because it's yeah, let me do from -10 to 10 increments of 1. Let me do -100, 100. See if that looks any better. Zoom out a little bit. Okay, we're kind of getting it there. Let me do zoom fit. Zoom fit, which is number 0 at the bottom of the list. That'll kind of that'll kind of help out with the graph a little bit if you want to get an optimal view of the graph. But so there's the graph. It's a linear equation, as we could see. And remember, this, you know, if we look at the problem, this was an increasing line, and you can tell it's increasing going from left to right, and it has a positive slope. Right? Lines with positive slope are increasing, like this one. All right. So there's my linear equation that models this data. Nothing too tricky there, but that's what it is. So when you're doing that, you know, from a description of something like a word problem, that's pretty much the process. The first thing you want to do is identify which one's independent and dependent. And it's pretty straightforward. And then from there, it's just finding the order pairs, finding the slope, and then using either one of these linear equation formulas to find this, the linear equation for the data, or for the description. So on the next page, we're going to find a linear equation from a linear model from data in a table. So now we're actually going to do is we're given raw data. I'm going to make a scatter plot here just for reference, which we did in the previous section. And then we're going to find a good model using raw data points from this data that we have. Okay, so in this process, you know, the reason why I'm making a scatter plot here is because if you look here, we want to find a good model. And if you remember from the previous section, right, we want to find, you know, there's a lot of various models for a data, right? There could be multiple lines for the data, but it's not just finding a line for the data, it's finding the best line for the data. So we're going to do this by hand, and then we're going to show later on, we're going to extend on this idea a bit. So, all right, so the number of Apple stores are shown in the table below for various years. So this is the raw data. Raw data is the data that's given to you as you collect it or as you researched it, whatever. So we're letting, here's the variable's description, we're letting n be the number of Apple stores at t years since the year 2000. So t is the year since the year 2000. Okay, so I'm going to put t here, and n is the number of Apple stores. And n just happens to be right here. This is the number of Apple stores, and that's what n is. So this is already n. Now t is the year since the year 2000. Now this isn't the number of years since 2000. This is the year itself. So if I want to get my modified data, right? Let me just put a vertical line here. My modified data, or my, you know, my refined data, I should say. My refined data. So how many years is 2003 since the year 2000? Well, that's easy. That's 3 years. And 2005 is 5 years since 2000, and so on. So this right here, that's the data I'm working with. That's my data that I'm going to use to make my scatter plot. It's why it's always important to make sure you read the variable's description first. You don't want to make your data with the year. You want to make it with the year since 2000, because that's what t is defined as. Okay, so how do I make a scatter plot here? Well, again, since this is independent and dependent, here's t, Here's N. T is number of years since 2000. N is the number of Apple stores. All right. Now, you want to think of like an increment size here. All right. So 3, 5, 7, 9. So if I go in, if I go every 2, like if I go 0, 2, 4, 6, 8, 10, 12, that's probably a good idea. So I'll kind of do that as best as I can. So 0, 2, 4, 6, 8, 10, 12. I'm going to go one more. 15. And since this is going like 50, 100, 95, I'm going to go in units of 50 here. So I'll go like 50, 100, 150, 200, 250, 300, and right up here I'll cap it at 350. So again, by hand it's not going to be the best, but you get the idea. So my first order pair here is 3, 51. So 3, 51, that's roughly right there. Right. The next one's going to be 5, 95. So 5 is right here. Actually, you know what? I could do better for that first one. Sorry about that. The first, because 3 and this is halfway, so 3 is actually halfway. So let me do better than that. So 351 is like right there. That's better. 5, 95. That's going to be right there. 7, 169. So somewhere right in there. 9, 249, so that's going to be right around there somewhere. Let's see, 11, 321, and then 12, 358. Alright, so that's my scatter plot. Now, whenever you're doing something by hand, I'm not going to get a straight line here. It looks like it, but I'm not going to. You're going to want to look at this in your calculator. That's the most accurate. That's drawn to scale. So let's make a quick scatter plot with this data in our calculator. So remember, to do that, you go to Stat, Edit. There's the stuff from the previous section. So just hit clear at L1 like we did. Go over to L2, hit clear and hit enter there. Now type in the data. So 3, 5, 7, 9, 11, 12. And then L2, 51, 95, 169, 249, 321, 358. Let's turn our stat plot on. Enter. On. Y equals. Let's get rid of that. So remember, turn your stat plot on. Your second Y equals. That turns it on. Hit enter there. And just hit enter on. So now to plot this, make sure Y equals is cleared out. And then to plot the stat plot, you just go to Zoom and you go down to Zoom Stat, which is right there. So hit enter there. Alright, so there's my scatter plot. Much more drawn to scale. I mean, yeah, it looks comparable, but this one's drawn to scale. So now let me ask you this. I want to find a good model, right? I want to find a good model. I want to find a linear equation. So to do that, I need to pick two good ordered pairs. I have to pick two good ordered pairs. Now, which one, just by looking at it, would you say are good ordered pairs? Now, typically you don't want to pick the outside or the in, or you don't want to pick the first or last ordered pair. You kind of want to ignore those. You know, typically that's a good idea. You want to ignore the first and last ordered pair. But if I look at this data, you know, some of you might pick the second and the fourth one. Some of you might pick the third and the fifth one. And either one of those may be okay. That's fine. For the time being, I just want you to pick two order pairs, except for the first and last one. I'm going to pick the second and the fifth one. So let me just build upon this down here. So I'm going to pick I'll pick these two, the second and the fifth. And the reason I'm doing that is, let me just make a note down here. To find a good model, it doesn't matter which two you pick, as long as it is not the first or last ordered pair. I'm going to pick the second and fifth one. Some of you might pick the third and the fourth one, or the second and the fourth one. Any combination of those is fine. Either one of those combinations will give you a good model. All right, so this order pair, the second one is this one, right? And the fifth one was this one. So this order pair is 5, 95. And this one was 11, 321. All right, I have my two order pairs. Let's find my equation of the line. So my slope, now I have n and t, so I'm going to use n2 minus n1 over t2 minus t1. If you want to use y2 and x2, that's fine. That's okay. So n2, so this is the order of the data, right? First, second, third, fourth, fifth. So my second one is going to be, this is the second order pair, this is the first order pair. So n2 is going to be 321 minus 95 all over 11 minus 5. So, all right. So 321 minus 95 is 226. 11 minus 5 is 6. So 226 divided by 6 is roughly 37.6. I'm going to round it to the 10th place. I'll round it to 37.7. And so there's my slope. And again, I have two order pairs, so ideally I want to use the point slope form here. So I'm going to use point slope form. Which is going to be n minus n1 equals the slope times t minus t1. Okay. And I'm going to pick, it doesn't matter which one you pick. Now, just be careful here. I want you to be careful. When you pick the ordered pair here, it has to be, make sure you pick either this one or this one. Don't pick any of the ones that you didn't use. Pick from one of the two that you did use to find the slope. Okay, so I'm going to pick 595. That's the one I'm going to pick. So when I go through this, I have n minus 95 equals the slope, 37.7 times the quantity, t minus 5. Okay, now just distribute and solve for n. So distribute the 37.7, you're going to get 37.7t minus 37.7 times 5 is 188.5. So now just add 95 to both sides. That gets rid of that. So then I'm going to get n equals 37.7t minus 188.5 plus 95 is negative 93.5. Yep, negative 93.5. There's my linear equation. Well, there's the linear equation that models this data using the second and fifth order pair. Okay, how does this compare? Like, how does this, look with the scatter plot made? I can actually do that in my calculator. I could plot this line along with my scatter plot just to see how it compares. So to do that, just go to y equals. And if you type in the plot line you got, 37.7, now I'm going to have to use x here. It's not a big deal. Minus, same thing, 93.5. Then go to graph. There's my scatter plot with the line that I just found along with it. So you can see how this line goes through the second and fifth order pair. And it comes close to these order pairs pretty closely. So yeah, that's a pretty good model. Now if I used the third and the fifth order pair or the second and the fourth order pair, it'll probably still be good, but it may not come as close to the other order pairs as much as this one does. So it's up for debate which one's the best model, but just by eyeballing it, this does a pretty good job. So that's a pretty good job using these two order pairs. Just, take this note. As long as it's not the first or last order pair, you should be fine when it comes to making a good linear model for your data. Okay, so that's that question. So what if so I just want to make a few notes here. Like, it's usually a good idea to graph a scattergram, and the reason for this is to see if the data is in fact linear, like this. This data, I keep getting that glare on my calculator. This data is obviously linear. The plots, the order pairs seem to go linear, so yeah, that's a good idea. And it allows us to pick two good order pairs from the model so that the model fits the data overall. By looking at this, we could say, yeah, the second and fifth one, that looks pretty good. Or, the third and the fifth one, that looks pretty good too. Okay, so, that's why it's always good to look at the calculator scatter plot, because that is drawn to scale, whereas something drawn by hand isn't drawn to scale. I'm just doing this for reference. Okay. So now, well, that's nice. Let me ask you this question. How do we determine the linear model that best fits the data. Up to this point, all we've been doing is finding a linear model that looks good. You know, I'm eyeballing it, right? I'm just eyeballing which one looks the best. But how do we know which one is the best? Well, the linear model that best fits the data is called the linear regression equation, or the line of best fit. So the linear model of best fit is the linear regression equation. That's the linear equation that models the data as best as possible. That means you can't get any better than the linear regression equation. So, you know, so from going forward, when you're modeling data, you know, you could find a good model by just picking 2 points, but I can one-up you and say, you know what, I'm going to call and raise you on your good model. I'm going to find the linear regression equation. That's the best model, because I have the better hand than you do. You know, if you're playing poker, right, and you have a straight flush and someone else has a 2 pair, you know, they might think they have the best hand, but you know, you could one-up them and say, you know what, I have something better. I have the linear regression equation. So that's what this paragraph states. You know, a good model, you know, finding 2 good points is nice, but the linear regression equation is always preferable. I'd rather have a straight flush than a full house, or a straight flush versus a two pair, right? I would rather have that. You know, a full house might be good enough to win the hand, but I know that a straight flush is even better at winning the hand. It has a better chance. It's, you know, it's better overall. So, you know, calculating the linear regression equation by hand is a tedious process, but in Math 105 we will not be doing that. We're just going to use the graphing calculator to get the linear. We're going to use the graphing calculator to get the line of best fit. The line of best fit is the linear regression equation. So, to close out this section, we're going to look at one more example. Oh, well, my dots from the previous page bled through. Sorry about that. But we're going to look at another set of data. All right. And we're going to do a scatter plot of this data. We're going to pick 2 good points based upon the scatter plot. And then we're actually going to find the linear regression equation, and we're going to compare them to see which one is better. You know, we're going to compare how they, you know, how they compare to each other. All right. So now here's the variable's description right here. P is the percentage of American adults who smoke. And that's what this data is. So this is already P. All right. T years since 1900. Well, this is the year. So T is the number of years since 1900. So I'm going to write that right here. So 1970 is 70 years since 1900. 1980 is 80 years, and so on. 90, 100, 110. So my data is going to be these 2 columns right here. So let's make a scatter plot. So let's get y equals, let's get rid of that, and y equals, clear that out. Let's go to stat, edit, and let's type in our data. All right, so go up to L1, hit clear, enter. L2, clear, enter. Type in your data. So 70, 80, 90, 100, 110. L2, 37.4, 33.2, 25.3, 23.1, 19.4. Okay. And now let's plot our stat plot. So our stat plot is on because we just used it. And now let's plot it. We go to zoom down to zoom stat. Hit enter. There's our stat plot. Alright, so let me bring this over here. So let me just put that to the side. Let's look at question 1. Use 2 good points to find an equation of a model that describes the relationship between t and p. So looking at that, you know, when I say find 2 good points, I'm saying eyeball it. Now we don't care about the first one or the last one. So I have the choices between 2, 3, and 4. Now, all right, so I really only have 2 choices, right? I can either pick 2 and 3 or 2 and 4. Now, if I pick 2 and 3, that's not going to be very good. I could do better than that because if I picked 2 and 3, I'm going to get a line that looks like that. And that's going to miss out on 5 and 6 because I'm trying to find the line that comes as close to these points as much as possible. 2 and 3 isn't going to do that, but 2 and 4 will. That will get me a line that's as close to all the points as much as possible. So I'm going to use 2 and 5 just by looking at the scatter plot. So I'm going to use 2 and 5. All right. So I'm going to use 80, 33.2 and 100, 23.1. All right. So from there, find your slope, plug it into the point slope formula, and solve for n, or in this case, solve for p, right? Because the dependent variable here, you know, independent, dependent. My independent variable is t. My dependent variable is p. Right. So I'm going to use p2 minus p1 all over t2 minus t1. So my second p value is 23.1 minus 33.2 all over 100 minus 80. All right. So 23.1 minus 33.2 is negative 10.1 all over 100 minus 80 is 20. So take that, divide that by 20. I get approximately, well, I won't round it, I'll use the whole thing. So it's negative 0.505. That's my slope. All right. Now, I'm just going to use point slope form, right? Which is going to be P minus P1 equals the slope times T minus T1, which is, that's my point slope form. So I'm going to pick either this one or this one, remember. I'm going to pick this one just because, I don't know, I feel like it. So P minus, so P is 23.1 equals the slope, which is negative 0.505 times the quantity T minus, and T there is going to be 100. So P minus 23.1. So this times this is negative 0.505 T. This times this is going to, well, negative times a negative is a positive. So 0.505 times 100. So negative 0.505 times negative 100. I'm just including the sign so I can see it. That is going to be 50.5. And then the last thing, add 23.1 to both sides. gets rid of that. So up here, I'll write the final equation. So I'm going to have P equals negative 0.505T, and then 50.5 plus 23.1 is going to be 73.6. 50.5 plus 23.1, just in case you didn't believe me, 73.6. There's my equation. Now, that's the equation I found by hand. That's not the linear regression equation. Now, how does this compare? Well, let's go to y equals. Type this in. So negative 0.505 x plus 73.6. Graph it. There it is. Does a pretty good job. I mean, it's a little off from this point, but I mean, yeah, that's pretty decent. All right. Now, question 2. Find the linear regression equation using a graphing calculator. Compare this with the model you found in the previous question. So, to find the line of best fit, that's the linear regression equation. Here's what you're going to do. So again, we're not doing this by hand in this course, we're just using the calculator to get it. So you just have to press a series of buttons. So here's how you find the linear regression equation. So if you see this button right here, the stat button is the same button you typed in to get to the, if I hit enter there, I go to the list values, right? If I press stat, instead of doing that, if I could press the arrow over to the calc button right here, and if I go down to number 4 right here, see this thing called linreg? That's short for a linear regression. And it's in the form ax plus b, which is mx plus b. It's a linear equation. So if I go down to number 4 and press enter, now here's where some of you might see some differences. If you have a TI-84 plus, this is what you're going to see. If you have a TI-83, you're not going to see this. So just, if you have a TI-83, just hold off a second. So for those of you who have an 84 or an 84 plus, really all this is saying is that X data is in list 1, the Y data is in list 2, which it is. Go down to calculate. And it's going to spit out values for A and B. A, here's the slope. B, here's the y-intercept. So according to this, the line of best fit is y equals, so ax plus b, so the slope here is going to be negative 0.461 x plus b, which is 69.17. But if I want to actually use the variables p and t, I could do that. So that's actually going to be p equals negative 0.461 t plus 69.17. That is the line of best fit. This is the best line you could get for that data. You can't do any better than that. Okay, so if I had a TI-83, what would I do? I'll just write it here. TI-83 users. So when you go to stat and go over to calc and go down to linreg and hit enter, that's all the same. So once you hit enter on linreg, so enter on linreg ax plus b. So the next thing you're going to do, once you do that, you're just going to type in all you're going to see on your calculator is when you type in enter there, that's just going to pop up on a blank screen. This function right here. So you're going to type, so when you see this, right, when you see linreg ax plus b, you're going to type L1, comma L2, and then you're going to hit enter. So how do I do that? Well, it's really not that bad. So how do I do that? So L1 is right above the 1 button. It's right here. L2 is right here. So on a TIE3, when you go over to calc, go to linreg, you hit enter on linreg. All you're going to do is you're going to hit enter on linreg, and then linreg is going to pop up here instead of this if you're using an 83. And then once you do that, let me get out of that, you're going to hit, so to get to the L1 and L2 buttons on here, you're just going to, since they're in blue, you're just going to hit second 1, which will give you L1. Then you're going to hit comma, which is right here. Then second 2 for L2. And then you're going to hit enter. Now here when I do that, it's not going to work. But that's what you're going to do if you have an 83. So let me go back to my linear regression equation. I want to make a few comments on this. All right. Remember in the previous section how we were talking about in 2.1, remember I vaguely talked about it, how do you know if data is linear or not? Remember I talked about the linear correlation coefficient? The values of the linear correlation coefficient are between -1 and 1. Remember I said that? Well, here it is right here. R is -0.98. It's negative because it's going down from left to right. But and at 0.98, it's pretty close to the value 1, which indicates that the data is pretty linear, right? Remember, the closer it gets to 1, the more linear it is. The further away from 1, the less linear it is. And you could already tell that, you know, it's pretty linear. You know, that does a pretty good job. So now let me actually plot the linear, the best line of best fit here. Let's see how that compares to the line we found in part A. So in Y2, I'm going to plot the line of best fit. Remember, this is the line we found by hand, but this is the best approximation of the data. -0.461 x plus 69.17. Did I type that correctly? I did. -0.4618. Yep. So now graph. There's the line of best fit. You can see how it's, you know, just below here, and they kind of mesh together over here. But so, you know, both of them do a pretty good job. But this one down here, that is the one that you would ideally use to approximate the data, because it does the best approximation. They both do the job, but this one does the job slightly better. Whenever you're modeling data, you always want to use the best approximation, because, you know, you want your data to be as accurate as possible, right? You want your results to be as accurate as possible, so you want to use this one as opposed to this one. Yeah, so that's just how the one by hand and the one by the line of best fit compare to each other. Graph that. Yeah, there they are. So again, when it comes to finding linear equations, from a description, you just find the 2 points in there somewhere. From data, you're picking the 2 best points that look the best, and then to find the line of best fit, once you get your data in, I already showed you stat, go over to calc, go down to linreg, enter down to calculate, or if you have an 83, just after you hit linreg, just do second 1 comma second 2, enter, and it'll give you this same data. So yeah, that's it for this section. So in the next section, we're going to look at, we're going to start looking at how to incorporate a new kind of notation, which is called function notation. So we'll see that in 2.3. So that's the end of this video.